A very good morning to all. I welcome you on behalf of National Water Academy to the online training course on Google Earth Engine and its application to water resources. I am Dr. M. Selvabalan. I am working as a scientist E at Central Water and Power Research Station, Kadakwasla, Pune. My topic here is to extraction of bathymetry using the Google Earth Engine and Python and other soft tooling apps. I have made this presentation in three sessions. The first session we will see about how the bathymetry data is generated using a board-based system, and then we have some hands-on to process the data, the collected bathymetry data along with the satellite derived data to create an area capacity curve, contour maps, volume, sediment rate, etc. The session 2 I have explained about the process we have undertaken using a Google Colab platform and QGIS and with Surfer software, by which we could able to extract the contour and DEMs which are used in the bathymetry data analysis. In this third session, we have covered the water quality aspects, in which how a neural network is trained to learn the water quality classes and then classify the image or the satellite downloaded data as the in terms of the quality of the water resources. Now we will start with the first session, where I have explained you about the bathymetry data extraction procedures. In the first slide, I have just kept some indicative figures where you can see here, this is the brain drawn in terms of a digital circuitry, and here another equivalent way of representing it, which normally is called as a deep neural network. A neural network is a one which maps what your brain sees to a target identity and then stores it, and then in future when you present similar object to it, it could able to classify it. In a deep neural network, deep searching and deep learning has been given to the machine to learn. So in this particular circuit, what we have seen is a 4 input neuron, and you have about 12 to 13 hidden layers and one target vector. This particular deep neural network is what I have used in my study to classify a satellite imagery band data as an input to the depth data what is being captured using a board-based bathymetry system. So this is one particular depth, and I am relating it to some 4 bands of the satellite imageries, and I am teaching the network with the multiple combinations. So this particular number shows the input neurons, output neurons, and the number of hidden layers and the nodes in each hidden layer. Now the intelligence comes in, how do you connect these input layers to the hidden layers. So each layer, how you connect it with what learning function, whether it is by a sigmoid, whether it is by a linear, or it is a log linear, or it is a ReLU. Multiple learning algorithms. Once you get mastery in the neural network training, probably these all functions will become easy for you to understand, by which you could able to train the network, and you can teach your neuron with a relationship, which creates a relationship between this to this. Now similarly, you have to train at multiple points. And see, for example, this particular neuron DNN architecture I have developed for a reservoir in Gujarat near Bhavnagar. So in this case, we have bathymetry data collected. Those bathymetry data, this is a satellite imagery, and this is how the final output becomes. And the measured bathymetry, we have trained. Measured bathymetry is collected, something like this. I will explain you in the detail. And finally, what is required for the reservoir authority is an area capacity curve, something like this. So here what you see is the capacity. Here you have elevation, and this side you have area. Now this area capacity curve carried out based on the survey conducted by CWPRS during 2019, and this is the one which is conducted by Gujarat Engineering Research Institute, Gary, in 2017. And then this is the original area capacity curve. This data is very useful for the project authorities in planning the reservoir. Now, how the Google Earth Engine and Python tools are coming picture to make all this process simple. And that is the beauty of this particular tools in today's scenario. So here I have used and I have just discussed about Google Earth Engine, and you have been in the earlier sessions and the classes what you have learned so far. You would have been now comfortable with how to use Google Earth Engine. I have used another coding editor API, what you call it as an application interface. I used a Google Colab interface. So I found Colab very interactive and useful as Google Earth Engine editor toolbox. Whereas in Colab, I can work it on my desktop and the data security, all are ensured. Whereas in Google Earth Engine, you are posting your data into the Google server, and in case if some data, if it is something to do with the confidentiality or etc., we can work it on a collab and then just generate the model in your notebook, and then you can link the file in a Google Earth Engine. We will show you all this in your practical sessions. And GitHub is a application tool which is linked with the Colab, where we have all repositories of the codes available. With the username and a call, you can able to get access to these data, and you can run it using Google Colab. We will see one example in that also. I also used Earth Explorer engine, where for downloading the images for my studies. That is also another alternate to Google Earth Engine, where I have found very handy applications are available. This is done because the study I carried out was well before 2015, where the Sentinel satellites were launched, and I was not and Google Earth Engine was not of much use to us that time. The advantage of having Google Earth Engine is you have a virtual processor, a supercomputer rather, from your computer you get an access, and you have a huge data storage space. You have a powerful RAM and a memory and a processor to work with. So in that case, Google Earth Engine is no doubt the best tool for a simple applications, for a small codes and one or two imageries. Even any other tool like Earth Explorer is also useful. In the Explorer case, we have to download our data into our local hard drive. Say for example, a Sentinel image with about 13 bands of one scene will be taking around 500 MB or close to a GB of 1 GB of data. So you normally people don't like to store everything in their hard disk drive. So in such cases, you go in for Google, where you have all the data are available in a click away, and and it can be loaded in a very few seconds of time as per your processor's capacity. So this is the advantage. And I have also used European Satellite Agency's Snap tool. This is very useful tool where you can able to get the idea about how the the environmental or the input corrections are being taken up, that atmospheric corrections, that type of facility. So all the images what you get to use for comparisons doesn't come at the same environmental conditions, the atmospheric changes. So you have some control over that, and to eliminate the noises in Snap tool. This is also another like a sort of a mini GA software tool. Then I have taken a lot of inputs and application from Four Steps Training Solutions, which is a voluntary service agency who has provided a lot of neural network and machine learning codes, which were useful for me in making this presentation also. And the bathymetry data collection, what I have told to collect the bathymetry, actual real world bathymetry, has been carried out using HiPAC as well as IVA software. So we use HiPAC in initially. Now we have used in this particular study, I have used a software called as IVA, which was used to log the GPS and echo sounder data, which is explained in this particular presentation. We use yeah, extensively the QGIS applications. As I told you, the study started before Sentinel satellite data was launched, and hence we were very comfortable with QGIS and NRC Bowen portal DEMs and the bathymetry. This is the standard way what CWPRS uses in analyzing and processing the data. And we use Surfer. We have licensed Surfer version 13, and now you have multiple versions. Surfer is also similar to GIS, where we have a lot of flexibility in the analysis, data interpolation to produce area capacity curve, what we have shown in the first slide here, the area capacity curve. Okay. So let me just touch upon with what are the measurements we are like monitoring and looking forward, which will be useful to produce all these tools. So these are the areas we can use Google Earth Engine into the maximum. So normally in a water resource system, you call this portion as a catchment area, which contributes to, I think many of you know that, but those who are new to this domain, probably this will help them. So in a catchment area which contributes to the reservoir. A reservoir is formed by construction of a structure across yeah, structure across stable mountain spaces, by the structural design. So now this water storage area will get water by this particular catchment area. So in the catchment area, what are all the measurements you look forward are the parameters related to weather, which contributes to rainfall, etc., etc., and the evapotranspiration. Now, Central Water Commission is hugely planning and working on the evapotranspiration model, which was not a parameter in the earlier water resources accounting softwares or the methodology, and hence we encounter a lot of error in there is a gap between what is the water available and what is being estimated. So the new models are going to work with availability of all the advanced tools. So this topic also is very relevant in today's scenario, because maybe before 2015, before the advent of GE and the European satellites availability, you don't have such a data availability. The scientists who wanted to work to predict such a huge catchment area characteristics don't get data. And if at all they are given data, they don't have a processor. See, your normal computer cannot even take about, even if you present it with 1 lakh data with the neural network to train, the network will hang. So present capacities, you have a virtual machine. You are getting a supercomputer with the GE environment, where I could be able to use 13 bands, each band with around 2 lakh data samples of Sentinel data, and all the 13 bands I can use as an input to train a regression model in my neural network. So this is the beauty. So this topic is relevant in today's scenario. However, maybe some 5 years back, this is just a discussion topic. Today it is becoming practical. So all the participants are benefited. Whatever you learn, you can put into practice, and then you can really bring it out as a national important output project. And hence you have to take a interest in learning all these tools, though there is no doubt about it. Now the second part here is the reservoir, as I said. So in the reservoir side, you have a level, gate control, the dam structural monitoring, which I call it as a dam instrumentation. Again here evapotranspiration, then the discharge, and then the flood modeling, flood mapping related activities. So which I have shown it here. This is the reservoir area, this is the catchment area, this particular portion which contributes to the reservoir. So all the zones you need a measurement. You can measure certain things, and if you using the modeling concept, you could able to predict certain things. And in a dam structure, again, you can able to measure the characteristics of the structural stability, etc. And we can, this modeling will be a successful one. You will understand this once the slide progresses, how machine learning and an artificial intelligence is going to be the tool which can, without which you could not able to go closer to any of these parameters we are discussing here. And in the outside dam structure side, you have water level. If it is a river, for flood mapping, you want to measure discharge. If it is a canal, you are interested in seepage. Then how the data is to be transferred to a place in case if there is a powerhouse, then the water to the farm. So all these are to be monitored. So the how much water will be available are all predicted with your MI and ML and machine learning concepts. Now presently engineers are struggling in the real world by this type of thing. This is the most latest technology people use today, an acoustic Doppler current profiler to measure the discharge in a flowing stream. You can see here this much amount of effort. You have to have a bow tied with a GPS and a multi-frequency acoustic signal sensors, and it is to be pulled across the river. During flooding season, you cannot even imagine going near to it. So these are all will work in very comfortable working conditions. So to have a these tools like AML will, but these data are important data. What you are doing it here in a normal domain situations with a beautiful and properly selected machine learning algorithms, you can able to predict the same using Google Earth Engine Python tools in a situation where a huge flood is occurring. Okay, so this is similarly, I have shown a photograph of a canal model where the measurements are being taken up. So as we discussed today, all these processes can be monitored. As far as all the conditions are good, you could able to get a 10 meter of resolution. Even Sentinel gives you 10 meter to 30 meter variable resolution for different bands. And with the satellite repetitive visit periods of around for 5 to 10 days, so I have put an average of about 7 days repetitive. So this is all in normal conditions. In case if there is a huge cloud cover, you cannot assure this 7 days repetitive, but still you have a huge data available for training and tuning your network for the prediction applications in the coming days. So yeah, this is been discussed already. Why this topic is relevant today? Because we are dealing with the data volume of such a huge set of data volume, and the credit not only goes to GE platform and processing. We have to give a credit to the NVIDIA GPU CUDA platform, where they have cracked the processing capacity a huge way, and it is made available to the common person to test it and train it from our local system. And Python has really made a resolutionalized change with all the functionalities and mathematical models applying at the back end, and which is available to us at a free of cost. So this is going to be a the success stories for our all the discussions what is going to follow up here. And artificial intelligence it requires huge data, and huge data requires huge processing capacities. Huge processing capacities is possible with the graphical programmable interface GPUs instead of the normal i10 i7 processors will never able to give you this amount of GPU capacities. And the basic idea of doing all this type of mapping in our the upcoming slides depends on the basic concept known as the feature extraction and mapping, which goes into a deep neural network. So these are all the main keywords which made all these topic relevant and possible for us to discuss here. Now here if you see, this is an apple, and the apple has been the features of the apple. Instead of storing the apple as is, the features of the apple, the color, the texture, the shape, all put together are stored separately in a storage, and the combination of the storage is being put into the memory of a deep neural network. So the combinational search, so it need not always have all availability. So you may have this, whereas this is not available, this, but still the system could able to predict this is closer to 50, more than 50% close to an apple, so I can call it as an apple. So for which you need to understand more of these neural network concepts and fundamentals, but which is not in our scope here. But this is how the identification and the mapping is all possible. The basic point is it is been put into multiple parts and been stored. Okay, so I'll be taking up some of the basics of acoustic bathymetry. Then we have another bathymetry which is in a very popularized stage today, a resistive bathymetry technique. The Chinese used it in a huge way, and is trying to adapt it. By this method, you could be able to see the sedimentation layers below the bed of a reservoir to a depth of more than about 10 meters or so, based on the research publications. And you could be able to get an idea about what type of sediment layers are deposited. This gives you an idea for the capacity assessment as well as for planning the dredging solutions. Then this is Google based image processing to get the depth information. This is purely a research topic, but then this particular methodology we have adapted and proved very successful in the canal bed mapping. Like, when the canal is flowing with full water, we could able to process an image file to get the bed profile of a canal, by which we could able to see is there any sediment deposit is happening even the water is in a flowing condition, as well as in case if there are some seepages etc. also can be pointed out. Then the fourth one is the satellite derived bathymetry, which is what I'll be explaining you in detail and with some practical codes also. Yeah, the role of Google Earth Engine is been already covered to you by many speakers in the earlier sessions. So I'll be not wasting much of the time in this. Artificial intelligence, machine learning. Yes, we will see some of the case studies. Then the all these things are covered, and since I am not going detail into it, application program interface, and especially via Google Earth Engine supports, you all know that Java as well as Python, and both the tools are presently supported, whereas Python becomes more popular in nowadays. And the advantage of Python is for an electronic engineer, we have now micro Python codes available. So what you are seeing in a computer-based tools are now becoming a small code and sitting inside a micro ICs, and then it is becoming a hardware application protocol also. So this is more interesting. Actually, what you are now doing is on a computer, but when you go to a field, you cannot carry such a huge big code with a computer, because many of the processes to be tapped and monitored through a small sensor, which will be in a size of a mobile phone or so. Say for example a gate controller, which will sit on a gate, monitor how much the gate is moving and then opening it in case of flood, which needs a very intelligent coding, which should go into a small ICs with a smaller space. So Python could able to crack that, and micro Python is also. So this is going to be the future of the programming, no doubt about it. Then possibly one or two case studies if the time permits. I will take it out at the end. One reservoir and one at a coastal. We have actually tried the satellite derived bathymetry technique at three places, reservoirs in India. And for in the coastal domain, we tried it at Andaman Lakshadweep Harbor Works, because you need a lot of data to validate the model also. So we validated with the bathymetry survey carried out by Andaman Lakshadweep Port authorities, and some water quality studies also we have classified for Calcutta Port Trust authorities, and to Goa, where we have got access to the measured dissolved oxygen and suspended sediment. Which probably is not my topic today. So maybe in the My colleague will be taking the water quality aspect, so I am not going into it. So those who are new to it, and this is the process of sedimentation takes place, where you will be losing your storage capacity, and the sediment is expected to settle down and then move further down. And in case if you have a hydropower house, it is not only reducing the capacity of your storage, also the particles move at a very high velocity and damage the turbines, etc. So it is to be monitored, and it should be stopped, and it should be removed also in some cases if it is necessary. Now the satellite based bathymetry survey, what standard Central Water Commission or CWPR is so far doing, is based on a imagery collected at a surface imageries. So the surface imageries will see the reduction in the catchment, the water storage boundary space reduction. However, it does not see what is below your MDDL level, the storage which is being eaten away here. So to map this or to measure it, you don't have a method other than putting a reservoir, a boat on the top of the reservoir, and then measure what depth is reduced. So that is the way. So this is normally as per the International Hydrography Organization standards. These standards are regularly updated. So as per the S44 standards, which is very detailed explanation of what type of GPS, what accuracy, how, what provision you have to make. All details are there. The basic concept is you have your survey vessel. Survey vessel is fitted with your GNSS, Global Navigation Satellite System receiver, which get an access to the satellites which are available on space. So the popular satellites what we use, we'll see it in the next one. The concept is, so a position information is very precisely acquired by the boat. So once the boat position on the move, because the boat is not going to be stand still while taking the measurement, it is being fitted with an echo sounder at the bottom, and there is a software controlling all the process. The echo sounder transmits the sound beam, and the boat is moving. So the boat moves and the sound beam goes, touches the floor and comes back. Some sound gets reflected at this particular point, some goes down, some goes to the bottom. So what you see as a graphical output after the measurement is not the original, it is a process data. The original data will go through a lot of reflections. Now what the board measures is the time taken for the sound to be ejected at this point to it reaches back. So what you are getting is the time taken divided by the speed of sound will give you the depth. Now the boat movement, all those things has to be compensated for your quality measurement, and the bottom submerged materials are also to be taken care, otherwise you will be getting multiple echoes. This is a multiple echo, so this is read as a larger depth actually. So the sound goes here, takes a reflection, takes back, and comes back. So what happens is this amount of travel time is assumed by my sensor as a deep zone. So it measures that this particular reading is going to be, say for example, 20 meters compared to this reading is going to be 10 meters. So at this point I will be reading it as a 20 meters. So 12 meters of error I am making. So all these, this is one particular point. Like this, you will be getting about lakhs of points in a reservoir, about 1 square kilometer also. So you need a lot of processing. So the data what you use in the final calculations are not really the measured one, they are the processed one. So how accurate is your processing is going to define how good is your bathymetry survey. This is the point to be remembered. So a third party, if you hand over the data, he will just collect the numbers and give it to you. Those numbers are not going to be useful numbers for your analysis, are not going to reflect the truthness. So you need a lot of experience in this particular data analysis. And yeah, technically if you are good in this, knowing these tools and how to use it, you could be able to get a position accuracy in terms of centimeters, and even your depth accuracy in terms of centimeter level. So now this is a GPS satellite system. Similarly, you have GLONASS from Russia, then you have Chinese satellites, you have French satellites, and many satellites. India also have their satellite but not available for the commercial use. So with this many number of satellites, say for example at a time you will have an access to see more than 30 to 40 satellites at a time. But they logically, for the mathematically also, you need minimum 3 to 4 satellites to get your position accurately fixed. So all other satellites are just for a cross checking, cross verifications, or you can say that if one data is not of quality, you can always cross check with others, so sort of things. So to measure the depth, you have acoustic, that is sound. Another one is resistive, that is a electric current going, and then based on the resistivity, finding out the depth. Then a remote sensing based mapping. And you need to have a lot of mathematical tools in processing it, as I said, based on the difficulties. So technically we go in for a geographical information system, so which is a very popular thing, RGIS, QGIS, IGIS. There are many softwares. We need to sometimes develop our own mathematical models because of the availability of the neural networks and the deep neural network tools. You can create your own tool because every reservoir the same model is not going to work. So the generalized softwares are not going to be a good solution, and they are about tend to fail, and they are going to give generic result, not accurate result. So have an accurate result, you need to have your own math models. So for which so with the advent of Google Earth Engine, MATLAB, Java, Python programming, with the measured bathymetry data and satellite imageries, we can create our own model for say for example Satanur Dam. We can have our own model for Indira Sagar. We can have our own model. Based on that, depends upon the water quality parameters, sediment characteristics, sound speed, the temperature, water, all these aspects will give you a good model by which you could able to use that model, tune for it. This is not a very big deal, but you need a lot of information about that local reservoir. So what I mean to say is a generic GIS software will take your result accurate to an 80% accuracy, whereas adding a math model to it will bring it down to a 90 plus accuracy, 90% plus accuracy. And with all this repetitiveness with Google Earth Engine and Python, you can go still better, further and further. Because I said the position accuracy I am already giving you with the satellites with centimeters, and depth also I am giving you in centimeters. In such cases, you could be able to produce a very quality area capacity curve, or the storage capacity, or the sediment rate, etc. These are the sensors which are used in the boat. This is an echo sounder. This is the sensor which goes inside water. This is a GPS tracker of Leica. There are many models. This is sound velocity calibrator. You need to know what speed the sound goes, so there is an instrument to calibrate it. So now when the boat runs, you are expected to produce the survey lines like this, and the data is collected here. So this gives you an idea about how a survey is carried out, and you get the results. So as I told you, the satellite owners are Navstar GPS from US, Russia has GLONASS, and China has Baidu. India has satellite not in commercial use. Then Japan, and so there are Galileo. The very popular available satellites are Navstar and GLONASS, which are more than for anyone to use these two data to get an accuracy in centimeter level. Even for the land surveys, it can go in further down to centimeters also, using a RTK GPS, real-time kinematic. I mean, it's not our interest of discussion today, but that itself is an area where you are required to install a benchmarking, referencing, etc. These RTK technologies are going to give you an accuracy in terms of even millimeters also. Okay. So these are all some augmentation satellites. So the references, more people are comfortable with GPS, then DGPS they call. DGPS is differential. So the differential means you will have a reference system keeping outside. Now, if you have the reference system also incorporated into the satellites, which are geostationary, then it is called as a SBAS system. Augmentation. So the augmentation can be from the ground control by you, or it can be made available in a satellite system itself, so that you get a reference corrections also from the satellites. Not in the same GPS satellites, it is all the reference satellites, separate satellites. So those satellites will have a coverage. So yeah, US has for their own area. Say for example, India has for their own area. So similarly, so VAS is the wide area augmentation system. This is for US zone. It covers only for corrections for only US. Gagan can give it for India. Similarly, for every country have their own augmentation system. So here, this photograph slide will give you how a survey boat is used. A small boat also is okay for us to do the survey, but keeping the security aspects. And the echo sounder, what is used by us, this is for a defense lake in OT, where the original storage capacity or the bed details were not available. So we were expected to use a dual frequency echo sounder. I'll explain you in detail. So the channel 1 gives a depth of 0.88, channel 2 is giving a depth of 3.57. So what does this difference shows? At this particular point, you have about 2 meters of silt. Now, when the boat moves on and on, so every point you will be accumulating such type of two depths, and when you integrate depth 1, you get a live capacity, and when you integrate depth 2, you get a original capacity or the silted capacity. So the difference will give you the amount of silt available. So this particular reservoir, it was very interesting because based on our measurements, actually the reservoir got dredged up also. So here you can see the dredging activities being happening. So this is a float and suction type dredger with a pipe. It is sucking the sediment material and then it is pumping it out. And after dredging, we verify the bed level change using a RTK GPS. As I told you, RTK GPS gives the elevations also in centimeter level accuracy. So there we have a ground control reference station, and you have a manual way of taking the elevation data. So all put together, then the dredger will produce you with the dredged volume based on his load of mud being removed. So all these three will to be tallied. Now the calculation what you made by the acoustic measurement, the field measurements what you carried with RTK, and the load material of sediment being taken away by the lorry load, all should match. So it matched, and hence the payment was made to the contractor without any much difficulty. So such systems are recommended. Such type of cross checkings and verifications are important and recommended for any reservoir which is going for sediment monitoring and dredging. So basically it is a bathymetry survey with multiple techniques. So in bathymetry, you have multiple ways of measuring the bed. So there is something called as a single beam. The board, this is a National Defense Academy board given to us to carry out a multi type of survey technique. So this is very unique. Nobody have done such a survey anywhere in, I think, in India at least. Are using all the type of measurement techniques in one boat in one reservoir, and then compare the results. That's going to give you a very interesting idea, and then you can say, with this experience I can able to tell them which methodology is going to be beneficial for what type of reservoirs. So CWPRS has done this, and we produced an output based on this, which could able to give you a guideline sort of thing. A single beam is a one beam just going at a point and then comes back, then the board moves on, then at the next point takes a measurement. So in between portion is not measured, which is mathematically modeled and analysis. Then it is single beam dual frequency, which we have seen in the case study here. Single beam dual frequency, where you get at the same point you get two depths. So this is for sedimentation applications. And in case if the reservoir is large, people go for a multi-beam, where a swath of beam. So means you are not missing out any points. Even if the board moves on, the continuous movement is being tracked. I'll show you with some photographs in the coming slides. There is something called as a sub-bottom profiling. Then you have something called as a side scan sonar. Then you have hydrophone. This hydrophone is an instrument. It picks up the underwater noises and the disturbances. So with all the measurements, if you can able to do some mathematics with this hydrophone data, you could able to get a quality output data by removing the noises. So this picks up noise. This picks up only noise alone. All other instrument picks up noise plus data. So noise plus data minus noise will give you only the signal, which is the bathymetry. So the true bathymetry. So this is a single beam bathymetry in a pictorial view, where, as I told you, the sound goes down and then touches the bottom and comes back. You have GNSS, Global Navigation Satellite System, which includes GPS, GLONASS, etc. The survey vessel moving in, and you get measurements at a point of beam, single points. So in between, if there is, so how closer you decide, is the accuracy you get. But in case if you have a large area to cover, you cannot waste your time like this. So you will be covering a 1 square kilometer of reservoir for about more than 2 3 months is not acceptable. So you normally go with a larger interval. So you will be missing out some points. So there are some trade-offs to be done. And the depth data is acquired something like this. So you get, so here using a high-pack software, we could able to show this demo data carried out by CWPRs in Kadakasla. So the boat traveled path, you can say 2.6 meter, 3.3 meter, 4.1 meter, 4.6. So these are all the data which we use it in our satellite direct bathymetry for training my network to predict the other depths. So this is the boat traveled path. These are all the gridded data which is used in the software for analysis. Here you see this is equally spaced data. This is like, as the boat moves, it is not in a logical way. So wherever, so practically your boat cannot go on a straight line. It will move on its own way as per the site conditions, and you acquire the data and then you mathematically interpolate it in a gridded form. So lot of mathematics. So what you measure it 5.7, but what it becomes may be different. Based on that mathematics go with so many other algorithms. So it may take the average of 1 2 3 4 and then put it. So all these things are the hidden truths. By if you understand this, you will produce a quality output. Then single beam dual frequency, you will appreciate this idea. Now first beam has taken this output. This one is studying dual frequency. One has come from here, another one comes from here. So this is the live storage with the silt. This is the hard rock bottom. So when we see a hard plot, it becomes like this. So you can able to see at particular area how much silt up is taking place. So this is a multi-beam. So here if you see, you have a continuous mapping. So it is a swath. It is either by beam forming or interferometry. So, so one keeps a center beam. From that it takes a mathematical calculations of the side beams. Other one is a, you just sweep your like a camera sweeping from one end to another end. So this that is one way, and another one is having multiple sensors and then seeing all at a time. So you can able to see the complete width, but this is on the surface of the sediment layer. So this is very useful to have a the live storage capacity estimated, and you cover a wider area. So normally with our practical equipment, we have seen about 100 to 200 meters of swath is being covered with such technology. So you can able to plan your survey grid lines of about 100 meters or 200 meters, and in between the data is logged automatically. So in case if it is a single beam, you will be getting only this. All these are missed. So that's the point here. Then subatom profiling. Subatom profiling, the main technology is like you give a different energy to your pulses and a different frequency. Frequency 1, frequency 2. Now frequency 1 plus 2 will have a different penetration. So this is the sound physics, but anyway, let us not get into it. But basically what it gives you an idea is the absorption and the reflected energy tells you whether what type of material it is. So the classification is taking place with the human expertise. Now this particular knowledge, the human expertise, the input parameter, the human decides from this reflected echo strength to say it is a sound, sand, gravel or rock head is to be put into your machine, because the huge data when it is taught to a machine, like it is typically a classification problem what is being taught to you in the initial classes in the GEE, where you classify the water body, land mass and urban area classification. And the similar way, this is something like this is urban, this is another village part, this is water body, sort of this type of the machine will understand with the features, and then automatically when the boat runs on, it says there is a rocket, there is sand deposit. So maybe it may look little difficult now, but when you start putting your hands into it, into the classification and artificial neural network, you find it is very interesting. Then the side scan sonars are used to, normally it is for, we used it to find out the cracks or some damages on the concrete structure on the dam wall. But then you can able to see, this is the sensor what is used to see a photography view of the bed in both the sides. Okay, so this can able to give you a very precise, like a small crack in the dam wall also can be monitored. So this is a very important required parameter. Even Indra Sagar they expected there may be some seepage taking place and may, so we used side scan sonars to inspect it. Okay. So we have seen this, like already explained the limitations of this, and CWPR has a quite a very good experience in carrying out so many surveys so far, and we have produced so many reports out of our studies. And every study, maybe it is a bathymetry, but then the requirements were different for different people. Somebody is interested in sedimentation, somebody is interested in the sediment movement, sediment rate, somebody wants to know the deep pockets to take more water, somebody wants to go for number of islands and many things. So every study has a thing, but under National Hydrology Project, we have carried out some three reservoirs. Now in Jharkhand, we are asked to do a sedimentation survey for one reservoir and predict the other two reservoirs with the satellite techniques, so that in future, in a satellite imagery, in a scene which is having about hundreds of reservoirs or water body, only one water body will be surveyed and remaining will be predicted by teaching the algorithm what is this absorption refers to. So we are going to make a breakthrough in the coming months. If we prove it accurate, then all the water body measurements will be carried out at ease with the satellite derived bathymetry techniques. Okay, we have already seen this. This is a resistive bathymetry output. Resistive bathymetry. Here you can see below the bed you can be able to go about 50 meters or so, and then you can see different resistivity indexes. So now you have to teach your machine this resistivity index corresponds to what material, this corresponds to what. So if you can see the alignment, it is a properly, it has mapped, the resistivity index has been mapped very nicely. So this is the way the bottom profile is expected to be. Only thing is we don't know what it is, but we know the resistivity index. Now when you feed it and call this is a marble, or this is a yeah, rock, it is iron, then the system will again classify it accordingly. So this is the beauty of these training tools, which requires huge data and processing power, which is available to you in the Google GE environment. Okay, so the technology involved, we have seen it. So now the data processing analysis, this is what the course is all about: QGIS, GE, and Python. Okay, so role of satellite. So here, what way the satellite data plus our bathymetry merges together. Both are not competitors. Both are complementing agencies. Now this is an Indira Sagar reservoir having about 900 square kilometer water spread, which I could able to acquire from a satellite imagery, IRS imagery actually. The external contour which is corresponding to 900 square kilometer at an elevation of 247 meter. However, when the survey was planned, the water availability was only on the orange line, which corresponds to a water spread of about I think around 200 or less square kilometer at an elevation of 233 meters. Now, when the survey work was taken up, the water level was at a different, water spread was at different level. Sorry, this 247 is not FRL, 262 is FRL. So water available during the survey was this, whereas we are expected to, this survey was designed like that from FRL to this MDDL, a satellite based bathymetry, and from bottom to this particular orange line is a boat based bathymetry. So this particular survey lines, when you get into the reservoir with the boat, the water is available up to this point, so you don't know where to turn your boat, right? So to understand where to turn your boat, you need to have this line. These are imaginary lines, but with the advent of the satellite data and the image processing toolbox, I could able to stop my boat. This one survey line is around 10 kilometers or so. So it's a quite wide, very larger line. So you will see everywhere water. So you, unless you don't have the line, you'll be wasting a lot of time traveling here. And carrying out one line survey will take about 1 or 2 hours, because your boat cannot allowed to move at a speed more than about 8 kilometers or so. That's a very high speed. 4 knots is a 3 to 4 knots is a recommended IHO recommended survey about speed. Okay, so these are all the difficulties in the practical survey. So what we advise is do a survey for a smaller portion using the satellite bathymetry technology. You extract the bathymetry for the whole reservoir and it will go very close. It will be very accurate. Okay, so this is the processing done. So now once the data is collected, you fit it with the boundary data, extract the contours and the volume, and then you plot your area capacity and volume data. This is for Mahi Bajaj Sagar Reservoir in Rajasthan, Banswara, which is completed very recently. So I have given some of the findings of the data. Now resistive bathymetry we have already explained. The technology goes like this: you have current electrodes and you pass a current into water which is in a very low milliampere level, and you map the resistivity indexes of the water is a constant resistive, so below water. So here if you see around 4 5 meters below, up to 4 5 meters water is there, so there it is shown as white. Below water you have a resistivity indices. So this is how your electrode array produces this type of resistivity absorption plots. So this is a practical field study we carried out with the resistivity sensors at a lake in Pundi Lake at IHA Institute of Hydraulics and Meteorology, Pundi, Chennai, Tamil Nadu, where we have seen the quality of these output, and we could able to plot the data also. This is also quite interesting. Now the data what you have collected will be a resistivity, and then you have to give the resistivity with other parameters and train your neural network. This is a simple neural network. You have some 4 inputs, and if the 4 input combinations will form, and then you classify it as a sand or mud. It's a 2-point classification. So here we have explained the neural network fundamental. This you need to understand to use it or write a code in Python to say what is what. Now the basic idea here it is, if the intensity is 1 and the relative speed is another 1, salinity, all these combinations, it will go to this point. This is a hidden layer H1 and this is an output layer, the combination null search. So so what weightage is to be given to intensity to understand this as a sand, for a speed to sand. So some parameters. So this weightage decides which parameter. See, you may have 4 inputs, but all the 4 inputs are not directly proportionally contribute to this decision making. They have been added with a weight, and this weight matrix is getting tuned based on the teaching set of data you are giving. So now I'll give from Kadakwasla reservoir certain values of these parameters, then I'll give it from another reservoir from Madhya Pradesh. So there, maybe the speed and salinity content are different, so the weightage will get adjusted. So you create a model which will become more or more generic. So it doesn't go by a specific number, it goes by a weighted number. And hence, neural networks are proven to be the best entity to classify in the classification applications. Anyway, that's not in the scope, but just for your understanding. Now here, see, we could able to, with the 200 epochs, 225 epochs of training, we could able to say limestone and clay, two classifications with the resistive electrode. So this is an example carried out in a naval base at Pune. Okay. Okay, so now, the third one, what I said is from a satellite imagery, how you calculate the bathymetry profile. So this is at a Gagra river, where we have taken the imagery. So this is the bridge, what you have seen here. So this bridge, when in an image, when you take it, it is here, the image is here. So water is flowing and there are some island portions and all. Now there is a technology by which you put a camera at the middle and then you can able to capture the surface velocity, which has been picking up very fast, which is going to be one of the wonderful tool in the coming years in the flood monitoring, where a human cannot access to the site So the drones and these camera-based technologies are going to be the measurement tools. All these point measurements here. This is the calibration point. This is at Karnataka at Sakleshpur. You have the camera at the side. This is the camera. Here you have level sensors. This river streams will get a very high downpour and the water will flow up to this level. Now during installation, now we have installed in a very lean period, but then and the heavy flood passes on in few hours, so it won't get noticed unless otherwise you use your camera technique to monitor it. So here again we have used the that shell-based Python coding. So the advantage is I run it on my computer itself, but the disadvantage is I have to install all the functionalities like IPIP. There is a function to install every library, which is not required if you use a Google Earth Engine. That's the only beauty and difference I see it. Otherwise, such a simple coding I can use it in my own desktop terminal Python terminal. So when I run this code and feed in certain parameters, what I get is and I selected a line. I wanted to extract the profile of the line, and that profile is extracted. This is extracted, so 10.86 to this point. So there is an technology behind it, which even we are going for patenting on this. But with an imagery also, with the 2D imagery, I am extracting the 3D information, the depth. Okay, and here the accuracy is about 1 meter. Every 1 meter is the pixel size, or it is the resolution of the screen. If I have 1024 by 860 of your screen resolution, then I can get 1024 points in this width. So my screen resolution is the resolution. Screen is something like a satellite to see. Now satellites get you an image at 10 meter pixels. Similarly, my screen gives me 860 pixels here. That means I can get about 860 points. So here you can see that 800 and something. So yeah. So now this is the process in which the processing, the data analysis takes place. Once the bathymetry data comes in, a QGIS tool is used to extract the satellite data in terms of bands, clip the region of interest, normalize the differential water index, thresholding, raster to vector, fix the geometries, removal of unwanted. These unwanted zones are the islands and the other areas other than the water body inside the reservoir area survey. Then a final boundary polygon is generated. This boundary is used on the bathymetry collected using the boat. Yes, this is the boundary collected. You will appreciate it now. This boundary will have unwanted zones. So these are all islands. So in Mahi Bajar Sagar, we have noticed around 100 plus small islands. So in case, normally reservoir authorities does not mind including that. So normal surveys, we just analyze it with the islands inside it, because every island is about very small that way, but it contributes to it. So but the processing is really a technological aspect. So remove these islands by, it's not you have to convert the polygon to shapefile to a polygon to a raster to a point, and then you remove it. Some places what will happen is this there will be a crossover also, so that is a very challenging task. It won't be, see here it's all smooth contours, whereas here there is a crossover, so you have to separate it into two islands. And then there are technologies, maybe the latest versions of softwares will give you much beautiful features, but then all this we have explained in the practical part in my second video. Then we created this particular project is for National Nuclear Power Corporation. They wanted to understand the deep packets and then laying a pipeline. So the power plant is coming at this particular area. So deep zone is here. So overlaying a DEM over this will give you the dam and the land elevation, so you can able to guide them the pipelining route. So in between there are some hillocks, so you can bypass it and then bring it to this. And then this is a 3D plot. Yeah, so this type of outputs are very useful for them in deciding, this is a 1 meter contour. So now we have come to the satellite derived bathymetry basic principle. So now a satellite gets a reflection of the sun's rays from the top of water, and also some bands will be going to the bottom of the water also. And if you apply your intelligence, the ratio or the combination of bands put in a particular mathematical ratio will give you more clearer view of the water bottom particles. Now the satellite agencies using this snap tool, they take care of these portions, sun, glitter, adjustments, atmospheric corrections, all those things. To an extent, we can also do it if required, if you know the atmospheric conditions. Otherwise, you assume the data is free from atmospheric errors. So atmospheric errors are overcome only within the water. You have to handle it. So this is one particular example seen where a Sentinel-2 of 250 square kilometer is used with 13 bands, 10 to 60 meters of accuracy, 5 days revisit period. This is at Bhavnagar. So this is the reservoir which is taken up for these trials. This is the scene. So here you can see this is a Shatrunji reservoir. So by applying a small code, very simply, a small code will give you the little bit of considerable accuracy. In case of the mathematics, if you improve on it, you get a very considerably a very high accuracy. That's the point. So the mathematics is going to play the intelligence part. All other things are tools being used. So Google Earth Engine is not doing anything, Python is not doing anything, but the mathematics creates the relationship between the measured bathymetry to the satellite reflectivity coefficient. So now once the band is acquired, we get a graded bathymetry, like the absorption coefficient values from minus 364 to 987. Now the measured bathymetry value, when I map it with the neural network and then say this is this, then it converts the whole bathymetry uh, graded bathymetry to a satellite derived bathymetry value. So where the it is converted, the gradation has been converted to a 5 meter to 9 meters of range. So that is the technology what we are talking about. Now once if I have validation data, I have validation data for this reservoir. Now I can predict the depth information for all the water bodies in these 250 square kilometers. So what we are trying to bring out at this point is, by doing a survey in one scene, you can get the water availability in the complete scene. So the time, cost, and you save a lot of your manpower in this particular process. Only thing is we need to ensure the accuracy here. So that ensuring the accuracy is completely depending upon the network or the mathematical model what you generate. But the information is hidden in the bands which you should know how to extract it. So to do that, we need to understand some of the basic physics of the multispectral information. This is for Landsat, but similarly, the bands are of similar nature for Sentinel also. So let us not get into that aspects. Now the breakthrough happened based on some of the literatures which was produced by the great scientists. The scientists have made the model in 1985 and 2003. And there is some modified improved algorithms are available in 2006 and 2008. But the point is, the Google Earth Engine and the Sentinel satellites were even launched in 2015. So the models were available even much before, but they were not having the data for them to validate it. So now we are fortunate to have both. We have a model, we have machine learning. So with this machine learning, I went further beyond this Su et al. And Stump model to get a much better accuracy in case of the Shatrunji reservoir. And thanks to Google Earth Engine collab and the machine learning support available. Before Google Earth Engine was given to us, I was fortunate to work with the Indian Institute of Tropical Meteorology Supercomputing Lab, where you have the same GPUs, the same power I was using live on the machines in Pune. Whereas after GE, you have a virtual machine available. So for everyone, you have an access. It is nowhere lucky guy is choice. Okay, so all this is the band ratio technique which is being taught to you. So basically what you are expected to create is you need to create a ratio between the absorption to the measurement values. In case if you can able to get a nice regression coefficient, then your measurements are going to be. So now here the data is sparse. So, but when you apply a proper mathematics of the band ratio techniques, you can able to see it all accumulated in one zone. Then you get a better accuracy. So this is a snap tool which we used in the pre-processing. Yeah, Google Earth Engine is already discussed and in detailing has been done. So I am not getting into it. This is on some of the outputs what we have produced in terms of water quality aspects, which is also, in a global scale you can able to produce this type of water indices. Okay, and yeah, here again this is also for near to Visakhapatnam. We had some data given to us, so for validation purposes. Okay, so this is another from USGS Landsat image. This is near to Tuticorin and Sri Lanka area where you have a graded bathymetry. So let us just go on, like we have, I think I am been taking the theory part. Let us go a little bit into the Google Earth Engine and then see what happens. Uh, so let us see from your Google Earth. I am just trying to get into GE and then run a small bathymetry code and then show you how whatever we are talking here makes okay. So I'll get into through some link now. So okay, so now over a simple code which we will share you also through the repository. So what I will do is so this is a very simple code with the Landsat data to use to see the bathymetry aspect. So let me come to here. Okay. Uh, so here what I am trying to do it is uh, let me select some zone here now, and then I'll run this code. Let me just run this code. Okay. Okay. Yeah. This code says the geometry is not defined. Yes. Okay. Okay. So now I need to select the geometry. I think how to run the code are all already taught to you, so I am not taking up that because the initial sessions very detailed, they have covered it. So now I have selected some region near to in Tamil Nadu. Now I'll run this code. So whatever we have discussed earlier, like so now the whole scene, you have created uh, the absorption coefficient to the bathymetry information. So let us see. Now here what it is happening is it's a graded bathymetry. Here you don't have the measurement value. So let me just go to the inspector and then see. So it is showing 1.14 is the pixel absorption for a particular band. Right now I am using band 3 and band 2 data alone. Band 3 divided by band 2, and I am using it. So you will appreciate it. See, in the land portion there is 0.97, whereas within the water you have a gradation. It has become 1.14. So this is the beauty of it. Now I have to teach this value to classes of different depths which are measured in a neural network. If I do that, I could able to get this particular 1.14 will become the actual depth, which I have shown you in the earlier I've shown you in the earlier slides. So the gradations will become more predominant. So we'll come back to the presentation here. Okay. Yeah, here. See, now this 1.01 will become actual depth. So yeah, so that's what I was trying to show you here. Um, So now how, so the same thing is being tried with the, see there is another tool similar to Google Earth Engine. You have European Satellite Agency Copernicus Open Access, through which also you can, but all these tools will download the data into your, so this is for Andaman Lakshadweep Island data. This, all these things will download the data into your hard disk. So you'll be losing a lot of your space and your, so that people, and time also. So now Google Earth Engine made this life simpler. So this we had done some time back, where G is not very popular without Python interface and all. So now it's no doubt you go for G with the Python interface. That's the a better option altogether. So this is the bathymetric data near to the port area, which is given to us for verification purposes. And see, the basic intelligence is the ratio, band ratio. So with the different bands, what is the absorption coefficient, I have to fit in the best model. So now the data has to be brought in a grouped manner, like, you know, you have 13 bands, you play with that and then bring in the best combination of the bands so that it all get grouped together. Then you make a nonlinear regression. So here it is a linear line. So when you, if you can fit it with a nonlinear line, you are mapping the absorptions for that particular band combinations. So this regression, this is the more patentable research portion of the study altogether. So everybody can map a bathymetry, but they don't get the accurate depth what I am trying to get. Or you may get better also with the better methodology. So this is what is to be understood now. So you can see that the reflectivity here to the actual measure, values, depth values, 0.4 meter to 1.17, and here it is a gradations. Okay, so that's the technology all about. So here you can see the legend bathymetry, because if we trained a deep neural network by putting the depths in classes 0 to 4 meter, 4 to 6 meter, 25 to 193. So so the complete 250 square kilometer area of in 2019 data we could able to map it, and you can see the contours also being generated. Okay, so we even produce the error map between what is measured and what is calculated by us. In the measured and training zone, almost the data is it is almost as close to the original one, maybe a millimeter, 5.4, maybe 5.6, that type of errors. But the non-measured zones, we don't know what is the actual depth, but that is to be validated, that type of thing. So where see the red marks what I shown is the depth is more than 1 meter error in the measured zone. There are some portions that was attributed to the tidal effects, because the in the image what I captured has that this is a coastal zone. You have to take the corrections of the tidal information also. In the reservoirs normally this is not a problem. So we have not trained for the tidal correction. If you train it for that, you get a better accurate results. And see the see now here it is a linear fit for the complete data, whereas I expect a fit like this, or the data all brought in a closer loop, something like this. So here it is a best fit. This was the fit we acquired for Shetrunji Reservoir, but whereas in Andaman coast we got it something like this, because we have limited data. It's all data processing only. Now see, this is a very important slide where you can see only the band 2 to the measured one has a relations like this. And when I applied a model, this is a model which we have developed in my research work, I could able to get a very closer fit. So this model is all 100% better than this or this or this. So with my model I could able to get the depth accuracy in even centimeters, whereas in this, in a deeper zones you have a good accuracy, whereas in a 5 to 20 meter zone you have a very sparse. So this probably you will appreciate. In case if this concept is clear, you can say the bands have a relation to the depth, and then that is the bathymetric measurement. Okay, so this is for another zone. So here you can see the observed value and the predicted value 9.59, 9.42. These are all in errors. This is in a pixel level, zoom level. So 10 meter pixels with the sentinel data. So you'll appreciate it. So probably those who are further interested in taking up such studies may contact us, CWPRS, and we can able to help you out, because we need a lot of trained manpower in this zone to have multiple combinations to get better and better results. Yeah. So a lot of processing involved into it. So in conclusion, I see these satellite direct bathymetry is an effective technique for assessing the coastal as well as reservoir. Very small samples of ecocenter bathymetry is required to train the network if your model is accurate. Yeah, so here you can see these band 1, band 2 sentinels downloaded data, band 1, band 2, band 3, band 4, band 10. X is latitude, longitude, Z is the measured depth. So you will appreciate this, you know all these things. Now band 1 to band 10, every band does not contribute to the depth. That is where the intelligence comes in. Maybe say for example band 6 may inclusion of band 6 into my neural network will degrade my learning. So I should know which bands are contributing to the depth, which are not contributing. So that is an optimization problem. Yeah, as I told, I was fortunate to work with the Pratyush supercomputing facilities available at IITM, Indian Institute of Tropical Meteorology, where the same GPU concepts, processors I have used. The same is now given to you free of cost in freely available for you in Google Earth Engine. Yeah. So now the optimization of the bands I have done with the yeah, technology called as a random forest training method. I think let us not get into it, but this goes by, this is an optimization method by which it says these are all the bands contribute, band 1, band 2, band 3, band 4 contribute to the output data what you have measured as a bathymetry. So if you do that, let us eliminate which are not contributing so that you won't be wasting time in training your network. Okay, then when I trained with the regression model, I have found for a lower depth there is a huge error, right? So this XGBoost algorithm did not work well for me to get the accuracy. Then we changed the learning models in my neural network. There are many learning algorithms between the models: sigmoid, tan sigmoid, ReLU, rectilinear, Gaussian, so many models. So we used combinations of sigmoid and ReLU at that's by lot of trial and errors, and we optimized 13 hidden layers. These are all based on some trial and error with some mathematical logics. Then finally we could able to find out uh, extreme gradient boosting support vector machine with RBF kernel gave quite a good amount of accuracy. So in case if you are using ML or logistic regressions, you will be getting around 60% accuracy. So your depth. So what do you mean by this accuracy? This with good accuracy I get measured and actually predicted by satellite at 1 meter depth to 5 meter depth. Everywhere you get a very close fit, even 1 to 100% fit. Only for the lower depths, yeah, in lower depths we have certain mismatch. This be attributed to the suspended sediment mixed up into it. So the training data set what you use should have you know the prediction time and training data set should not have a large differences. So after monsoon imageries if you take, it will be with highly suspended sediment and the color change which will attribute to your errors. So that also to be trained, you can train that also, but then so the logic is this: in case if the network is trained with all probable combinations, it is going to predict well. That's the meaning. Whereas another combination did not give you a accuracy, the measured and the modeled are the having different at all the stages, whereas here there is a match. So what I mean to say is every band combination will have a different type of matching to the so this is the most intelligent part of the algorithm. So logistic regression, lasso rich, there are many available. Python supports all those things. So here I got a very good root mean square error. So let us SVM RBF kernel, right? So I have already explained this ANN concept. So this is the network what we finally got for a bathymetry of Shatruji. This need not be correct for another reservoir within India also. So you may have to, but a minor tuning. Starting, this is can be a starting point and you can optimize it with this. Okay, so here I have shown my code, whereas which we will run it and then see it also in the hands-on part. So we used ReLU as I told you, and then Adam is the solver. So these are all available in as a function calls for you in Python coding. And I got a very good fit by which I could able to measure the bathymetry, the centimeter levels of accuracy errors. So multilinear perceptron is used here. And even the another important point is, like, the time based optimization using a GPU. I took only 5 minutes to run all the 13 band data in a Aditya high performance computing system, which was otherwise taking 48 minutes on a simple code to run just for a testing purposes. So that much amount you will be saving. And by measuring this reservoir data, we predicted another reservoir nearby, and you see these changes. So this particular data is not actually measured. We took the measured data from the field engineers, and then what has been predicted with the deep neural networks. There is a difference, but very well within the margin. This is a sample screen I have shown, 5.5 and 5. This is actually, this reservoir was not even seen by us. We only did the survey here. So that's the speciality of it. So you need to go for more of a non-linear fitting rather than fitting. So by this method, what do we achieve? I did a survey in 2017, but till 2020 or even till date, I can able to give the bathymetry change map with the old measured data. In case if we expect there is a huge erosion or sedimentation takes place, then another survey is recommended. Otherwise, 17 it was like this, and in 2020, and after 10 days, next imager I can say your reservoir profile is changing like this. So this is the beauty of the advent of all these Google Earth Engine, Sentinel satellite images available. And we have validated not only at Shatrunji, we have validated at Indra Sagar, a larger reservoir in middle part, and Kutiyadi in Kerala also. What is required for validation is you need two survey data to cross check it. So that is the beauty of it. So Indra Sagar CWPR has surveyed it twice. Kutiyadi also Kerala Engineering Research Institute has surveyed it twice. So we have for validation purpose also another data. So this, in conclusion, what I say is ground truthing is always required. So as IBS, so IBA integrated bathymeter survey cannot be removed. Satellite give the power to get an input data. Computers give the processing strength. ANN, there is some spelling mistake. Excuse me for that. ANN and ML allows artificial learning. Python, Java making coding simpler. It is possible to estimate the water availability comprehensively by this technique with GEE platform. Hence, planning of resources are more relevant. So not to waste time more on ground. So limited time for ground validation and process with that. Thank you so much, and we will see the hands-on in the following session, and the session 2 and 3 will give you the detailed explanation.